Hey, Mr. Harridan here. We're going to go over light. So here we go, going over light. So light can has abilities to be a particle. There are particle properties of light, and there are wave particles properties of light. Okay? That's why they consider light having a dual nature or split personality. Sometimes it acts like a wave, and sometimes it acts like a particle. Okay? Light as a wave here. The speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. That does not change. This is a constant. You'll learn in physics eventually that the only way you change the speed of light is you change the medium it's passing through. That is the only way you can change the speed of light. Because the speed of light changes if you're going through water as opposed to the air. Okay. Wavelength is represented by the Greek letter lambda, which is this upside down Y thing right there. It is the length between corresponding parts adjacent to crest. Okay, can use any length units. Usually it's going to be in meters or nanometers for us. Okay. Frequency is represented by the Greek letter nu. It is the number of waves or crests that passes a point per given second. This is why it has the units cycles per second, seconds to the -1, or hertz. All of those mean the same thing. It's the number of cycles per second. That is what the frequency is. Okay. Electromagnetic spectrum here. Visible light has a range of wavelength between 400 nanometers and 700 nanometers. Okay, the 400 nanometers is near the violet side of the spectrum if we're talking about visible light. The 700 nanometers is near the red side of the spectrum. Okay, visible light can be seen from 400 to 700 nanometers. Okay, so the shortest wavelength is violet, which is about 400 nanometers, and the longest wavelength is 700 nanometers, which is about red. Okay, the colors of light are in order from Roy G. Biv. Okay, not all light is visible. There is forms of light that is not visible. Okay, for instance, okay, here is our visible range right here. Okay, the ones with the longer wavelength here would be radio, micro, and then this is infrared because that's close to the red side, so that's how I remember that's the infrared side because it's close to red. Then on the higher side with the shorter wavelengths, that would be ultraviolet, X-rays, and gamma. Okay. Over here, this is the long wavelengths, as opposed to gamma, which is the short wavelengths. Okay. If you have a long wavelength, look. Ooh, long wavelength. This has a low frequency. Okay. As opposed to a short wavelength, which is like this, this has a high frequency. Why did I use F? I should have used nu, whatever. I should use nu. So let's use nu. So that's that cursive V there. Like that. Okay. Again, long wavelength. This is a long wavelength. Okay. That is low energy. That does not take much energy to do. As opposed to short wavelength, if you do this for a while, guess what happens? You get tired. You know why you get tired? because it's high energy. Okay. And they have this nice little saying here: red Martians evade. Roy G. Biv using X-ray gizmos here. Remember that this is the short side over here, wavelength, and this is the long wavelength on this side. Okay, what mathematical relationship can you draw between wavelength and frequency? Long wavelength, low frequency, so those are inversely related. One goes up, the other goes down. What relationship can you draw about energy and frequency? Low energy has low frequency, so they both go up or they both go down, so this is a direct relationship. Okay, you guys are champions. The legend is out. If you can figure out how to stop this video.